All right, we're going to take a look at intermediate value theorem, the IVT. Here we have a little picture of what's going on. Consider that you have two endpoints from perhaps here to up here. Okay, you could draw but without lifting your pencil as long as the function is continuous. Okay, it doesn't say it has to be differentiable, but on your journey from one endpoint to the other, as long as f of a does not equal f of b, the two endpoints don't have the same y value, this theorem says that you have to pass through every single y that occurs between the low y and the high y, between f of a and f of b. All right, and there's that k again, it throws us off, but it just represents a y value that falls between these two y values of the two endpoints. All right, problem 1 says use the intermediate value theorem to show that this function has a 0 in the interval between 0 and 1. So this is our a and this is our b. Okay, so somewhere between the x value of 0 and x value of 1, we're saying that this function has to pass through the x-axis in order to have a 0. So all we have to do is we have to show what the y values are at each of these x values. So we're going to evaluate the function at 0. Plug in 0 everywhere you see x and you get a -1. So already we're aware that the point 0, -1 is on the graph of f, and -1 falls below the x-axis because of this negative value. So the last thing that we have to show is this y value at 1, when x is 1, is it a positive number? So plug in 1, and when you do that, you get 2. All right, so what we can say is that 0 is between -1 and 2, which just means we have to pass through the x-axis because of this negative y and that positive y. All right, let's look at number 2 with the data table. All right, we've got a continuous function on the interval -2 to 2. We're going to use the table to determine which of the following statements must be true. All right, does this function take on the value of 5? Okay, well, you might want to notice what the smallest y value is and the greatest y value. Well, the smallest y value appears to be -5, and the greatest y value appears to be 6. So does 5 fall between those two? It sure does. 5 is definitely greater than -5, and 5 is less than 6. So there has to be a y value of 5 if you were to plot these points and create a continuous graph. So this one's true. All right, is there a y value, a 0 of f of x, is there a y value between -2 and -1? So we need to look at the table, look at the x-coordinate of -2, look at the x-coordinate of -1, look at the y values. Because y goes from -4 to +1, we are going to have to go through all the numbers between those two, so that would take us through y equals 0. So that one's true also. All right, statement 3 is saying that a 0 of f of x is 6. So you could put that in point form, and what it's saying is that there is a 0 when x is 6. Well, remember, our x values just go from -2 to 2, so we don't have any information past x equals 2. So right here, I can't say that this has to be true. It might be, but it doesn't have to be true. Okay, we only have the data between -2 and 2. So at this point, I'm just going to choose D. 1 and 2 have to be true. All right, let's take a look at note card 7, average rate of change. All right, for this note card, we have a few formulas right here, and we have the background. Problem number 1. Okay, we're looking for the average rate of change from P to Q. So delta y over delta x with the appropriate units, and then we'll draw in the secant line. Remember, a secant line is a line through 2 points. Okay, so we're going to say the change in bacteria, whatever we want to use, B, okay, over the change in time. So instead of y and x, we're just using B and t, the difference of the two y values. So you're usually asked to show the work that leads to your answer. So you want to show the setup. 340 minus 150 over 45 minus 23. And it might be helpful to include units in your work. In this case, we have bacteria on top and days on bottom. All right, and performing the necessary calculations, okay, the rate of change is 190 over 22. bacteria per day. All right, and I would attempt to draw the secant line through these two. However, I don't have a straight edge that I can use with this, but I think you can see the average rate of change is represented by the secant line if you were to draw it in. All right, problem number 2. We have a function. We want to find the average rate of change for the first 3 minutes. So what we want to do is evaluate the function at 0. So everywhere you see x, plug in 0, so you get 30. Okay, that makes sense. At time equals 0, the ball is at a height of 30. Plug in 3 everywhere you see x. Okay, and once you do the calculations here and square the 3, multiply by 16, and subtract from 30, I think I ended up with negative 114. So that just represents that the ball dropped 114 feet. All right, so what's the average fall rate of change for the first 3 minutes? So it's just delta y over delta x. So f of 3 minus f of 0 over 3 minus 0. A difference of y's over a difference of x's. Again, you can include units in your work if you wanted to. This was feet and this was minutes. All right, performing the calculations, you're going to get 144 divided by 3, and when you simplify it, you get negative 48 feet per minute. That's the rate of change of that ball dropping from a height of 30 feet. All right, let's look at example 3. Notice we're presented with tabular data, so we went from a graphical perspective to a verbal problem and now to a table of data. Right, use the table below to estimate the rate of change, f prime, at 1870. Well, what we're going to do is we're going to take the 2 points on either side of it, okay, and use those with delta y over delta x. It would be perfectly acceptable to do 2 other calculations. You don't have to do all 3, just pick one of the 3. And what's appropriate is you can use the 2 points on either side of the year in question, or you can use the year in question with the point to the left, or you can use the year in question with the point to the right. All right, we're going to estimate f prime of 1870 by using the 2 points on either side of it. So delta y over delta x. Again, this is including the units in our work. Millions and years go down here. Okay, and it looks like once we subtract and divide by 20, we're going to get, oh sorry, this is positive, 0.94 millions per year. All right, part B, interpret the meaning of the value you found in part A. Okay, well, f prime of 1870 is the rate at which the population is changing in millions per year at t equals 1870. In millions per year at t equals 1870. Okay, well, based on the fact that we also know what the value is, we could respond a little bit differently too. We could say that this means the population is increasing because we got a positive number. We could say the population is increasing at a rate of 0.94 millions per year at t equals 1870. So Sometimes you're asked to interpret after you find the value of the rate, and if the rate is positive, then you know the regular function is increasing, and so that's why it'd be totally appropriate to say that the population is increasing at a rate of, and then continue from there. Sometimes you're asked to interpret before you find the value, and basically all you can do is just kind of respond like this. You don't know if the regular function is increasing or decreasing because you haven't yet found the value of the rate, if it's positive or negative, to determine that answer. All right, let's look at Cliff Note 8. Okay, instantaneous rate of change, or the derivative of a function. We have the background there. Okay, so it's about the language. What is the instantaneous rate of change at x equals 2 of this function? Well, that's just other words, using other words to ask you to find the derivative evaluated at x equals negative 2. So let's find f prime and plug in 2. This would be negative 2, since this is negative 4 plus 2. Okay, so the function is decreasing at x equals 2 because f prime of 2 is negative. All right, let's look at example 2. All right, this is the long way to find a derivative. It's the formal definition of a derivative. Okay, if it asks you to evaluate, okay, well, what you could do is you could do the necessary algebra. You could square, distribute the negative 2, distribute the negative 1 over here, clean it up, factor out the h, and divide with the h in the bottom, and then plug in 0 to get the answer. Because right now, as it stands, if you plugged in 0 everywhere you have h, you would get indeterminate. Okay, so that would require that we do the algebra. Of course, we could do L'Hopital's rule too. But as a third option, to evaluate this, if you identify this as a formal definition of a derivative, identify the function first, right here. So the fastest way is to go, well, I see that the function that I'm trying to differentiate to get the derivative of, okay, is present in the parentheses right here. This is f of x plus h minus f of x, so f of x must be the function here. So the derivative, okay, is 12x minus 2. So that's the answer. You could get this too by doing the long way, which is all that algebra. All right, and then what does this represent? We could put this as the derivative. Okay, or you could say this is the rate of change of f of x at any x. This is the rate of change of f of x at any x. I can find the slope of the function at any x. All right, problem 3. All right, in example 3, we're presented with 3 options of derivatives, supposed derivatives. Okay, so which of these 3 right here, any, all, none, okay, represents a derivative, a slope, at a? All right, well, we see here in first example that the limit as x approaches h. Well, what's wrong with this is that we don't have any x's in here. So as x approaches h, that doesn't mean anything to us. Okay, so that is out. That doesn't represent a slope on f at a. Okay, but look at 2. Okay, imagine that as x approaches a, you plug in a here and plug in a here. In doing so, as x, whatever that x value is on our graph, if it approaches a, we're really saying consider a point nearby a, f of a on the graph, and let x get closer and closer to that point as well. Okay, so this one right here is a correct way to represent a derivative. Okay, look at 3. As x approaches a. All right, well, there's no a in here. This looks like our formal definition, but you know, there's a misprint down here for us to choose it. Okay, this would be right and represent a derivative if we had h approaches 0. And likewise, what do we need on problem 1 for us to realize that that's going to be a derivative? Well, this needed to be something different. in order for this expression to correctly represent a derivative, then right down here at the bottom, okay, we would have to adjust and say that this is as h approaches 0. So the only choice is 2. B is the correct answer.